Hello, welcome back to lecture 7 of the series on tectonics and geodynamics. So, we are now going to go forward to look at more complicated situations of what we noticed on a flat earth. So, lecture 7, I'll be dealing with how three plate motions occur on a flat earth. Now, whenever we look at this, right, so the main concepts that we're going to cover is on a flat earth, we'll try to see the geometry of what exactly happens when we have three plates together and how the geometry of these three plates actually changes, right, with time as motion continues to take place along all three plate boundaries. So, to look at this, first of all, let's have a recap of what we looked at, right, and how we actually approach the case of plate boundaries. So, once again, so just remember the first basic conception is, again, just remember the things that we talked about. So, one is that if you've got a set of parallel lines, that actually talks about mid-oceanic ridges. When we have just a line, right, with triangles drawn like this, right, it talks about a subduction zone, and a transform fault, right, is just a straight line. Now, all three of these do not completely describe the nature of the boundary. We have to put in the velocity vectors for us to be able to make out exactly what we are talking about. So, in the case of the mid-oceanic ridges, if you remember, so we show them, right, as two sets of arrows equal in magnitude, opposite in direction on either plate. So, if this is plate A and this is plate B, we show the two plates moving away from each other on either side of these two parallel lines. So, the parallel lines are supposed to be exactly equal in length along the same direction, except that the azimuth is different. So, if this is moving towards the east, right, this part has to move exactly towards west. Now, what we've shown here is an orthogonal relationship. That means the relative velocity vector is perpendicular to the boundary. Now, it need not always be the case, but it is commonly the case. So, we will consider this as a simplistic form. We will consider this to be the case here. Now, the other thing that is important in each of these cases is just to realize that in the case of any person who is standing on plate A, right, we have plate A and B being created at the same rate at the mid-oceanic ridges. So, if this is being created at the rate of 2 centimeters per year, so B will be moving, any point here will be moving this way at the rate of 2 centimeters per year as new ocean crust is created here, and similarly on this side, new ocean crust would be created at the rate of 2 centimeters per year on plate A and would move to the west. However, to an observer on plate A, another observer on plate B will be appearing to move at twice that velocity. Therefore, the rate at which the new plate is being created may be 2 centimeters per year, but the relative velocity vector is actually twice that. So, what we talk about here, right, is when we are describing the rate at which plate is being produced, we call it the half spreading rate. So, this is referred to, if you remember, as the half spreading rate along a ridge. Now, this term, the half spreading rate, is used dedicatedly when we are talking about mid-oceanic ridges. So, the relative velocity between plates A and B is twice the half spreading rate. You can call it the spreading rate, but there can be some confusion because sometimes people actually tend to use the words spreading rate and half spreading rate almost in synonymously, so that can create confusion. So, the best thing is to talk about half spreading rate when we are talking about the rate at which the new oceanic crust, or more appropriately lithosphere, is being produced. And we also use the term relative velocities between plates A and B, right, when we are actually talking about the actual movement of one plate with respect to another. Now, when we come to a convergent plate boundary like this one, so these are characterized by a polarity. Now, what do we mean by polarity? It means there's a particular direction in which is important. So, in this case also, let's just call this plate A and let's call this plate B. So, if this plate is moving towards here at a particular velocity in this direction, plate B will be moving in exactly the opposite direction with the same magnitude. Okay, so the line will be the same, the direction of the arrows will be different. Now, if you remember what this means, we show this with with these triangles actually indicate the direction in which one of the plates is subducting. So, in this case, the triangles are pointing in the direction, they always point in the direction of the overriding plate. So, in this case, B is what we call the overriding plate, right, and A is my subducting plate. So, this boundary has a polarity, in which case plate A is subducting below plate B, right, and the two arrows will point towards each other. Once again, as in the case of mid-oceanic ridges, we are showing this in this particular case as the direction being completely orthogonal to the boundary. It need not always be, it can actually be at an angle, which means that there will be a component of motion which is parallel to the boundaries as well. Now, let us come to the third type of plate boundary. This is plate A and B, right. Once again, let us say this is a transform fault. In this case, the conventional way to depict the motion, right, is by having these two half arrows, right, two half arrows on either side to show the relative velocity. So, in this case, there is no divergence, no creation of new plates, there is no consumption of new plates, but what happens is that there is a conservation of motion. So, this is what we call as a transform fault, right. It can be in oceans where it is more common, but we do occasionally see transform faults in continents. Now, in each case now, when we are actually showing it this way, we talk about the relative velocity of one plate with respect to another, right. So, what do? We show it as a relative velocity, right, in this way of, let us say, of plate B with respect to plate A. Now, what this means is I am talking about the relative velocity of plate B with respect to A. So, in this case, if I am talking about the relative velocity of plate B with respect to A, right, that would be in this direction. For this case, when I am talking about the relative velocity of B with respect to A, it would be in this direction, right. And when I talk about the relative velocity of B with respect to A in here, right, the direction would be here. So, the length of these arrows in each of these cases is exactly proportional to the magnitude at which the relative velocity of the relative velocity vector, the direction points towards the direction in which the actual movement is taking place. So, this is the standard convention that we are following. So, it was just a recap, helping you to recollect, right, exactly what we were meaning with this. Now, let us go to the next one. When we talk about what we discussed in the last lecture, we talked about how plate boundaries can change, plates and plate boundaries can change with time. Now, one of the misconceptions that many of us start off with when we are thinking about plate tectonics is to think of them in terms of normal convection cells. So, something rises, spreads out and then sinks, right. So, the normal kind of thing that we seem to consider would be a cell a little bit like this. So, we see something moving this way, going this way, and here it is moving up, going this way. So, in each case now, this would be the way in which a mid-oceanic ridge would be operating as per us. So, for us, we tend to think of this being the descending limb, right, these two being the descending limbs, say, of two subduction zones, and this would be the place where upwelling is taking place. This is the spreading center. And we tend to think of these things as staying constant in time. So, if something is being produced, it is being consumed. So, all the time, right, the area of the plate on the surface of the earth remains constant. Now, that is exactly the thing that I am trying to say is not the case. As we saw in the last class, if you remember, we took these two plate systems. We took a plate, a larger plate, I think it was B, and then you have a smaller plate A. It does not matter what we were thinking. So, in this case, so if this was my mid-oceanic ridges, this were subduction zones. So, we can see that if these are spreading this way, so the boundaries here would be, sorry, the boundaries here would be like this, right, and here the boundaries would be this way. So, the magnitudes of these relative velocities would be exactly the same. The length of this line and the length of this line, the length of this line, this one, all of them would be the same. The lengths of these two lines would be exactly half of these two lines, because these are the half spreading rates, right. So, now in this case, as we discussed different situations, the way I have drawn it here. So, if something like this happens, the rate at which the plate is being produced, if that is less than the rate at which the plate is being consumed here, ultimately plate A will be completely consumed within plate B, and we will end up with a single plate system. The opposite case would be if we found that the polarity of the subduction was just the opposite. So, if we can think of it this way, right. So, if we have it this way, so in this case what would have happened is, so if we have it this way, now this would be the overriding plate. So, plate, this is B, this is A, and this boundary of plate A would keep on moving to the east, right, at the velocity at which it is being produced, and as a result plate A, the surface area of plate A will simply increase with time. So, what we are trying to show you is that the way in which the geometry of these motions actually occur on the surface of the earth means that the orientations of these the geometry of these plate boundaries will actually change with time. So, the plates themselves and the nature of their boundaries also can change with time, as we will actually see. So, let us actually now look at specific cases. Now, these are cases where we just had two plates. It is easy to actually think of two plates because we can see the way in which these happen, and you also see the way in which we actually try to understand what the nature of the boundary would be. So, it is the orientation. Once again, just to recollect, if there is a significant component of motion that diverges away from the plate boundary, then you have divergent boundary. If you have a significant component of motion which is in which the arrow is pointing towards the plate boundary, then the plate boundary is convergent, right. On the other hand, if we have a significant component of movement which is actually parallel to the plate boundary, right, in that case it's dominantly a transform type movement. So, the three types of plate boundaries are actually characterized. These three types of plate boundaries would be characterized by the manner in which the relative velocity vectors, right, how they are oriented with respect to the plate boundaries. And as we go on to the next part of today's lecture, you will see how this matters even more. Now, what I will do is I will try to change this off to a black thing. So, let us just move on to the next one then. So, we will now begin to think of specific cases, right, which are slightly different from the things we have talked about, right. We have talked about a two plate system, as I talked about before. I just showed you, recollecting from the last class. Now, let us just think of a more complicated system. So I am just using my very poor drawing skills because I think that would give you confidence that there are people who can draw worse than you, and it does not really matter how badly you draw as long as you can actually convey what you want to convey. So, let us now think of a three plate system. Okay. So, let us think of three plates like this, right. And if you draw badly as I do, then let all of this give you hope that you need not be a great artist to be able to understand this and to convince others about what you understand. Now, let us just think of a system like this. So, we have a three plate system. We have plate A, we have plate B, and we have a plate C. Now, these three plates, right, have boundaries that are orthogonal. These are orthogonal, but these boundaries are different. So, the boundary between plate A and B here and the plate A and B boundary here are different. They are orthogonal to each other. The boundary between plates A and C is along this line, and so while it is not completely correct, the boundary between plates B and C is also along this particular line. Now, let us give ourselves some space, right. Let us assume now that the half spreading rate along here, along this boundary, is 2. That is, the relative velocity of B with respect to A, right, is 2 centimeters per year. Okay. This is not the relative velocity, sorry, the half spreading rate is 2 centimeters per year. So, the half spreading rate would be 2 centimeters into 2, which would be equal to 4 centimeters per year. So, the relative velocity between these two, plate B with respect to A, would be 4 centimeters per year, and therefore, the length of the line can actually be depicted by a line which is 4 centimeters long and it is pointing in this direction, and the whole of this arrow must be placed on plate B. So, it is placed near to the plate boundary, and it shows this arrow, for example, represents the relative velocity of plate B with respect to plate A. This side on the other hand represents the relative velocity of plate A with respect to plate B. So, we have two different things being shown here. Likewise now, so it is spreading at the rate of half spreading rate of 2 centimeters per year. So, the relative velocity is 4 centimeters. So, half spreading is 2. Now, if I go along to this particular boundary, now this boundary is actually, if I now draw the relative velocity vector, so it is 4 centimeters per year. So, I have to draw a line which is 4 centimeters long on plate B. Now, in this case again the relative velocity vector must be exactly the same between the same two plates, because plates are rigid bodies, and if their plates are rigid bodies, it means that the relative velocities, no matter where you take it on the plate, will be the same, right, for one point on a plate with respect to another fixed plate. So, in this case there, this is the way in which it would operate. So, you would get a transform movement along here, right, and this value has to be at least 4 centimeters per year. Now, let me just give you one other extra bit of information which you actually need. I am telling you now that the relative velocity between plates C and B is such that the relative velocity vector is a dextral transform fault. So, the relative velocity vector between these two is parallel to the orientation of the plate boundary between plates A and C. So, if I say the relative velocity of C with respect to A, let us say that that is equal to 3 centimeters per year. So, these are all realistic sort of values that I am giving you, right, and it is telling you the relative velocity between plates C and A. Now, sorry, I mean I have told you about the AC boundary. What I actually wanted to talk about here would be the AB boundary. So, what we really need to know is what is the nature of this boundary, right? What kind of boundary is it, right? Is it a convergent boundary? Is it a divergent boundary, right? Or is it a strike slip boundary? This is something that we need to understand, right? And how do we actually see, right, how the AB boundary would move to an observer on plate C, right, if we can make that out. So, these are the standard questions that would come in, right, when we are trying to actually frame a question based on this kind of diagram. Now, let us just think of how we would proceed to do it. Now, we have got two sets of relative velocities. We have been given the relative velocity of B with respect to A and the relative velocity of C with respect to A. Now, what we need to find out is the relative velocity of, say, C with respect to B, right. So, all of these, now these are all relative velocities, so, and vectors. So, I should show them this way. So, what we need to find out is this value, right. So, the question is now, how do we proceed to solve this particular problem? How do we now begin to analyze what the relative velocity of C with respect to B should be? Now, in the previous examples, we could just use normal common sense to actually work out exactly what the rate of consumption would be. But what do we do in these cases where things become a little more complicated? So, what we can do is now just rethink this system and this just try to find out exactly what we are trying to determine. So, we are trying to determine the relative velocity of sorry, what did I say? It was B with respect to C. So, let's keep it consistent. So, it is the relative velocity of C with respect to B. This is what I want to find out. Now, we then use, when we find we have a problem like this, what we do is to use standard vectorial techniques, and so we use just vector addition to be able to analyze this. Now, the easiest way in which to write this is to see this as the sum of the two known vectors that we have been given. So, what are the two known vectors we have? We have the relative velocity of B with respect to once again, let's talk about it this way. So, the relative velocity, we keep plate B here. Now, let us assume that plate B is where we start off from, right. So, it would be relative velocity of B with respect to plate A, right. This is something that has been given to us, plus another vector which is the relative velocity of c with respect to plate A. Now, this is the standard way in which we show this vectorial addition. So, if we want to find out the relative velocity of c with respect to B, right. So, if we go back to the previous slide, so the relative velocity of c with respect to B. Now, c with respect to B, c with respect to B is we want to understand what the velocity would be along this particular region, right. This is what we need to understand. So, to understand this, now we have to go back to this, the relative velocity of A with respect to B, right, A with respect to B. Now, keeping B fixed, A with respect to B, so B on the other side, right. We write it in such a way that if you now if you imagine these two together, so B would be at this end here, C would be at this end here, A would come in between. So, in one case, A is the moving plate with respect to B. In the second case, A is the fixed plate with respect to C, when we have to write it in this form. So, this is the easiest way in which you can remember this. This is just a way of remembering. So, let us just begin to work out the things. So, once again, just to go back, harp back to this little diagram we had. Right. So, you have this. Now, once again, I am forgetting the nomenclatures. So, this was B, this was A, and this was C. So, when you have something like this, this is 2, right, this is 4, right. Now, this was 3. So, how do we now begin to work out what this boundary would be like, right. So, once again, this is what we are trying to understand, what would be the relative velocity between plates B and C. So, first of all, let us just try to work out what the relative velocity of A with respect to B is. This is A with respect to B. Now, the way I would do it, the way I find simplest to do it is just to assume a fixed point here. Now, I assume that this is the position of my fixed plate B. So, I am an observer on fixed plate B. Now, I want to see, right, which way plate A is moving with respect to me. Now, if I am an observer on plate B, right, to me the plate A is actually moving westwards at the rate of 4 centimeters per year. So, I draw a line this way, right. So, this would be a line which has a length of 4 centimeters, right, and it is moving to the west at this rate. The next thing that we have got to do is now let us say my observer now moves from here and sits on the position which is indicated by the position of plate A. So, A is at this end. So, this is the vector relative velocity of A with respect to B. So, the arrow is pointing in the direction of the plate which is moving, and the fixed point, the base, the tail of the arrow indicates the direction or the fixed plate from which we are moving. So, now we have to add the next motion, which is the relative velocity of C with respect to A. Now, C with respect to A is given here is 3 centimeters per year, but this is a vector which is actually moving in this direction and has a length of 3. So, what we need to do is this point here would be A, this point here would be C. So, we just take this and move it to this relative velocity triangle, and then what we do is to place this point A here, just draw a line of 3 centimeter length, in which this point, this represents the vector C with respect to A, right. This point here represents C. Now, what this now means is I have now got 2 of the velocities. Now, to an observer on B, which direction is C moving? So, you can see where C is. C would be moving southwest. It is moving southwest with respect to C, and it would be, right, the velocity would be, the relative velocity would be proportional to this length. Now, this is a simple enough geometry, right, by applying Pythagoras theorem. So, you have 4 centimeters per year here, 3 centimeters per year here, right. It is not drawn to scale, so do not take it very literally. So, obviously, the length of this line must be equal to 5 centimeters per year. So, what we will see, to an observer on plate B, plate C will be moving to the southwest at the rate of 5 centimeters per year. Now, so this would be the relative velocity of C with respect to B. Similarly, the relative velocity of B with respect to C would be this way. So, this would be point B, this would be C, and to an observer on plate C, B would be moving to the northeast at the rate of 5 centimeters per year. Now, on this, how do we make out the nature of the plate boundary here? Now, the thing to do is what we see here, right, is the plate, the direction in which plate C is moving with respect to B. Where do we place this arrow? Because it is now absolutely vital as to where the tail of the arrow and the head of the arrow will be. Now, the rule is that the head of the arrow, will always be placed right on the plate, which is actually assumed to be moving. So, in this case, what we do is we take the head of the arrow. So, this 5 centimeter length will actually go on to here. So, we take this. So, this arrow pointing this way would indicate, right, that this is the relative velocity vector of plate C with respect to plate B. So, with respect to plate B, right, and this is the AB boundary, BC boundary. So, plate C is moving towards plate B, right, at a rate of 5 centimeters per year, and it would be in this direction. Now, as you can see now, similarly, right, we can just take it in the opposite direction, and we can see the relative velocity of B with respect to C would be in the equal and opposite, right, it would be in this direction. Now, either way we draw it, you can see that the arrowheads are pointing towards the plate boundary, but they are not orthogonal. So, first of all, it means, right, that the nature of the plate boundary must be significant convergent with strike slip component. Right, that is for certain, right. It would be significantly convergent, but with a strike slip component. What is not clear, however, right, because this information is not given to us, is what will happen to this plate boundary with time. Because to understand that, we need the polarity of the plate boundary. We need to know whether B is subducting below C or C is subducting below B. Unless this information is given, I cannot actually understand exactly how things would change with time in this particular figure. So, what do we do now? We have to think of these two situations. So, one situation would be in which I put something here. So, you have the relative velocity of B with respect to C. Let us assume that B is now subducting below C. So, C is the overriding plate. Now, if C is the overriding plate, this is at the rate of 5 centimeters per year this way, which means a component of it would be moving in this direction. Now, B is being produced at the rate of 2 centimeters per year along the AB boundary. The rate of its convergence here, right, the rate of its convergence here would be exactly equal to that. So, how would this change with time? So, we need to work out what exactly the geometry would be if this changes with time. What would happen if the opposite were to take place? So, suppose now that the plate boundary, right. So, the plate boundary is just the opposite, right, and C was subducting below B, that is B was the overriding plate. In this case now, in this case there would be a problem now. In this case, B would consistently now be produced along this particular boundary and would actually be tending to move towards the east, right. So, now with time then C and B would not remain collinear any longer. So, with time then the configuration of this boundary will actually change. So, this means now that we have got some idea, right, of exactly how plate boundaries will actually move with time. So, it tells you now how to work out the nature of a plate boundary. Now, to understand this a little bit further, right, we need to go some steps forward, right. We need to actually look at what kind of boundaries we can actually think of, which can be a little different from the things we have looked at. So, let us actually look at a different type of plate boundary, right. This, let us say that the boundaries here now would be orthogonal, right, but they also, let us assume that a couple of them are collinear, right, not all of them. So, let us assume now again a 3 plate system, and let's assume that the 3 plate system is like this. We'll keep the plates similar to what we called them before, right. So, this is C, we'll call this one A, and we'll call this one B. Now, let us assume, right, that there is a plate boundary here. Now, let us now think of different ways, right, different ways in which we can actually work out what happens here. Now, let's say that we've been given some information. We've been given the plate velocities between plates. We are given velocity of, say, A with respect to B, right. So, A with respect to B, let us say this is equal to 4 centimeters. Let's put it like this, e to the power minus 1, now the standard way in which we depict. And we have also been given, let us say, the relative velocity of C with respect to B, which is, let us say, equal to 6 centimeters per year. Okay. Let us say we have been given these two things. We have been given the relative velocity of A with respect to B and the relative velocity of C with respect to B. Okay. So, these two are what we have been given. Now, what are the ways? Now, we have just given you the magnitudes. What about the directions? Now, let us say that A with respect to B or B with respect to A, right, it's this way, right. So, obviously, both arrows are pointing towards the AB boundary, right. So, it must be a convergent boundary. On the other hand, let us look at the BC boundary. Let us say that this is now a dextral strike slip fault, dextral transform fault, right, which has a length of 6 centimeters. So, this is 6 centimeters per year. So, it is a dextral transform fault, and what we do not know about is the nature of the AC boundary. So, the question that we are supposed to ask is, what is the relative velocity of C with respect to A? So, this is the question that we will try to answer now. What would be the relative velocity of C with respect to A, and how do we begin to work this a figure like this out, right? Now, to understand this, it would actually mean that we have actually got to put in our principles once again, same principles that we used before, right. We will have to put this in once again to understand exactly what it would be. So, in this case then, we talk about the relative velocity between these two, and then we, let us say, we assume that there is a boundary which is a subduction zone. Obviously, it has to be a convergent boundary, and in this case the way we put it is that plate A is subducting below plate B at the rate of 4 centimeters per year. So, plate A is subducting below plate B at the rate of 4 centimeters per year. So, the question that we have with us now at the end of this class is to try and work out what would be the nature of the plate boundary between plates A and C, what would be the magnitude and the direction of the relative velocity, which would actually then dictate finally what the nature of the plate boundary between plates A and C would be. So, the conclusions that we can reach on the based on the preliminary things we have done, we will continue this in the next lecture. So, we will talk about the main conclusions we can see. We can see that using relative velocity vectors, one can determine the nature of motion along a plate boundary. The nature and position of a plate boundary can change with time, as we can see, and the nature of the change can be determined using relative velocity vectors, but there is a caution here that you cannot, in the case of a subduction zone, you cannot really tell, right, which plate is subducting below which one, right, if you are just given the velocity information. That has to be specified, which one is the overriding plate, which one is the subductive plate. Unless this is told to you, you cannot actually answer this question. So, we will leave it at that today. So, you can consult Fowler's book for all of this, and thank you.